So yesterday we talked about how some of the reference standards are not really gold, and very difficult to know the absolute reality. So we do live in an imperfect world. So we did talk about this topic also, the different types of logic. So I'll just look at that. Deductive versus inductive reasoning. So in inductive reasoning, we use patterns to arrive at a conclusion. So we observe, we look at something, we see something, we think we recognize a pattern and then make a conclusion. And most of it is conjecture. Whereas deductive reasoning uses facts, rules, definitions, or properties to arrive at a conclusion. So here like in algebra, we start with a premise and then, or a principle or a rule, and then come to a conclusion. So it's a little more likely that what our conclusion is going to be true. Whereas for inductive reasoning, we have to be very careful. Both types of reasoning, we have to be careful. So this is the story that all of you know, the blind man using inductive logic and trying to, coming to a conclusion, and each one is coming to a different one. So really, this observation, this is a problem with when we don't know the absolute. Deductive logic also is problematic. So all cats have 4 legs, I have 4 legs, therefore I am a cat. So here the problem is you have to have all the premises correct. You have to have all the rules before you. You can't just follow one rule, because there may be competing rules or competing principles. So you have to have all the principles in front of you that are relevant. But more or less, deductive logic, if you have the premises, then the conclusion will follow. So this is again, for those of you who are interested, how difference between inductive logic, deductive logic, and the interaction between the two. I mean, this is I found on the net, so you can also look at it. So this is something that is, as thinking individuals, as rational human beings, we have to understand these things. Again, deductive logic versus inductive logic. So in deductive logic, like I said, you start with a premise or a rule and then you go to a conclusion, and it's more or less certain, unless you don't consider all the rules. So hopefully in the judiciary, the legal system, they try to use that. Whereas in inductive logic, like in most epidemiological observational studies, you say 90% of humans are right-handed, John is human, therefore John is right-handed, but not necessarily so. All crows are black, but even the 1,000th crow may be white. So the conclusion follows not with certainty, but only with some probability. So when you're using inductive logic or when epidemiological observational studies, we have to rely on probabilities, and their inference is risky. So again, this comes to the issue of validity and reliability. So validity is, accuracy or the truth, and reliability is, how reliable you are, or how consistent you are, how precise you are, repeatability. These are issues that come under reliability. So this picture again you may be familiar with, the marksman. Either you can be low accuracy and low precision, or low accuracy and high precision. Here this person is very precise, but he's away from the bullseye. Okay, so his accuracy is low. Whereas here there's high accuracy, because average is somewhere in the middle only, but not very precise. And really we need high accuracy and high precision. So this can be applied to many things, but also in diagnostic tests. When you're doing diagnostic test also, we have to see is it valid or not. So basically that's what we are talking about. The new test we are comparing with something, is it a valid conclusion that we come to? That happens only if the gold standard has to be absolute gold. If not, there's a problem, isn't it? So you may end up here if any of these things could happen. We saw this slide earlier, that we live in an imperfect world, we have to deal with uncertainties, and there's a lot of gray area. So what do we do? How do we proceed? Again, this, just to refresh you, the test characteristic, the 2x2 table, we are assuming that this disease and no disease classification is by the gold standard or the absolute truth, but it may not be so. Again, we saw this slide earlier. We saw this. So the use of the best technique in diagnosing the disease is technically impossible. It might be technically impossible. We would like to do it, but maybe technically we can't. We can't do laparotomy for everybody, or we can't do, something invasive for everybody. The best reference might expose the patient to unacceptable risk. So these are the situations where we might use an imperfect gold standard. So I'm just giving you examples, the situations where you might end up with an imperfect gold standard. For example, creatinine phosphokinase MB in serum, commonly used to approximate histology for MI. Even though its elevation occasionally occurs without MI and is not invariably found when infarction is present. So how do we know the patient really had an MI or not? So sometimes we use a gold standard which is less than perfect. Again, take an example of diagnosis of C. difficile. It's a new index test called latex immunoassay. So what would be the gold standard? What would be the gold standard? I don't know, PCR, culture. We have to ask the microbiologists or the ID people who are here. Maybe clinical and biopsy is the best reference. And I'm just giving an example, and it might not be that. So what would happen if latex immunoassay was compared with stool cytotoxicity test? So that's a question. Suppose we choose the wrong gold standard. What will happen? So, this is what in life, we have to always think, are we making a mistake? But not everybody is like that. No, we think we are absolutely sure, 100% self-confident, or is there a little bit of inward-looking, self-critical thinking, that there may be an error component, and we try to minimize that error component and try to get a handle of it. So this is what we talk about when we talk of a prejudice or bias. So its evaluation against an imperfect gold standard introduces bias, definitely. So the validity decreases. Whatever you say, sensitivity, specificity, all that loses validity if you don't use a proper gold standard. And this distortion can lead to gross overestimates or underestimates of the test characteristics. So everything is suspect. So when you look at sensitivity and specificity, what happens to that? The direction of the bias depends on whether the new test and the imperfect reference are on the same patients. Mistakes can happen with the gold standard, the so-called gold standard, less than perfect gold standard, or it could happen with the index test, either differing on the same patients or different patients, that we don't know. When this does not happen, that is conditional independence, the sensitivity and specificity will be underestimated. So if they don't err on the same patients, they are totally different, then it's called conditional independence. Several examples are there in the medical literature where an imperfect gold standard has been used. So this is another example. Evaluation of test performance with an imperfect gold standard. Okay, so this is the actual truth. This is the perfect gold. This is imperfect standard has been used. So, and you have test results. See what happens. You may get 98 here, 2 here, 18 here. This is the actual truth. But when you do an imperfect gold standard, you may get 94, 46, 22, 38. So, and then what happens to sensitivity, specificity? Sensitivity 98% here, 67% here. Specificity 98% here, 97.4% here. Predictive values, more or less the same, but there's some difference. So when the test and standard make errors independently of one another, the sensitivity and all can be very different from what it actually is. So the perceived sensitivity, yes.
Previously you talked about conditional independence. Can you please explain it? Conditional
See, either the new test and the reference standard may make the mistake in the same patients, or it will be totally different. Okay, so we are assuming that they are totally different. If it's on the same patients, it can go in one way. If it's on totally different patients, it can go another way. So it can go either up or down. Okay. But usually if it is conditional independence, you underestimate. It's basically saying they're independent of each other. So that's all we mean. Either they're happening on the same patients or they're on totally different patients, randomly occurring. Okay, so this is the perceived sensitivity of the new test. So here sensitivity of the true unbiased sensitivity. This is the unbiased or true specificity. So this, it becomes like this. What you observe, the A you get in the box into the true one plus B. So this is the formula that is there. I mean, just to try sort of understand. Or this whole thing comes down to this. Similarly, we can get for specificity. Depending on the truth specificity and the observed numbers, you'll have to derive this. So, I mean, you can consult a statistician who can, use the formula and come up with, try to get, what the error is or what the truth is. So the new test, this is the standard. The truth, this is what we are using now, the imperfect standard. But this is the formula that you will get. So what you find here has to be adjusted. Okay. Okay, moving on. Are sensitivity and prevalence independent? Sensitivity and specificity. That's a mistake. Are sensitivity and specificity independent of prevalence or not? That's a mistake there. It's specificity. Sensitivity and specificity will not change with prevalence of disease. This is the question that was raised yesterday. Will sensitivity and specificity change with prevalence? And I said that usually we say it does not change. Okay? But as long as the spectrum remains the same in the disease and non-disease groups. So sensitivity and specificity of a test will change if the spectrum is different. That is mild, moderate, severe, all that mixes, and also the commonly confused disorders. If they are all different, the case makes spectrum, that these are two terms that we talked about yesterday. If they are different, then sensitivity and specificity will change. When an imperfect reference has been used, the perceived sensitivity and specificity will change with the prevalence of disease. So this is normally it does not change with prevalence. But if you use an imperfect reference, then it will change with prevalence. So what's the effect of an imperfect gold standard? Just an example. Suppose the true prevalence of disease is 10%, true sensitivity is 90%, true specificity is 90%. Please draw a 2x2 table for a population of 1,000 people. Can you do a small exercise? Just how do you draw can you draw a 2x2 table? So what do you expect if the truth is there, if it's if you're absolutely correct that the gold standard is true, then this is what you should get. So suppose you do a new test, can you draw a 2x2 table? Okay? Done? Okay, you will get something like this. So 1,000 people. So you got total of 1,000. All the boxes add up to 1,000, right? Prevalence is 10%. So prevalence is 100 upon 1000, correct? Everybody got this table? Sensitivity and specificity are given. Sensitivity is 90 upon 100, specificity is 810 upon 900. So this is how you try to draw a table. When you read an article, you can sometimes, from what is given, you can get the table done. Okay, now suppose, why don't you repeat the exercise, the prevalence of 50% and 90%. Now what do you get? So suppose this table, this is what is the prevalence here? 180 upon 1000, no? So 18% about. 18%. So from 10% you have now changed to 18%. Now what is the sensitivity, specificity, likelihood ratio, all that you can calculate. I mean you can do it later, but you got the gist of it. I just want to know what you get if you change the. Okay, so the relationship between sensitivity, specificity and prevalence. So here the prevalence of disease going from 0 to 100%, and the perceived sensitivity, that means the sensitivity you get with an imperfect gold standard usually follows this curve. That means you will get higher the prevalence, higher the sensitivity. And perceived specificity goes other way. Lower the prevalence, higher the specificity. Okay, this is what we usually, if you do these exercises with the formula that we used, then it's, let's see, when Jay Siren is here, maybe we can do the exercise. Yeah, he's going to do the practicals for you. So
the assumption that in the imperfect gold standard, it is a random effect. It is not in the same patients, in independent patients. That is the assumption.
Yeah.
In that case, this formula.
The effect of prevalence, estimates of a test sensitivity are most accurate when the prevalence of disease is high, and estimates of a test specificity are most accurate when the prevalence of disease is low. That's what the graph showed. So we'll stop here, and I think we can have some time for practical exercises.